Is it the first time that you have classes here for any of you? Oh, for most of you. Okay. Who has had classes here before? Nobody? Okay. Okay. Also, it's my first time, so. Okay, so let's before we start, okay, to go back to do some refreshment what we covered yesterday. I just want to introduce here we have Marcus. Yeah, he's going to be the student assistant for this course, and he's going to answer all of your questions, hopefully, and he's going to clarify all your doubts. So he's the man to go. Okay. He already sent you a link on Blackboard to agree on the day, because we cannot have it exactly today after class. So to agree on a different date, okay, and time. So please answer to give because he will make a decision based on your answer, okay? So if you don't answer, maybe he won't take that into account, okay? So please participate in this. I think you did it in Doodle, right? So just give your preference, and then he can plan based on that. Okay. Also, one thing I remember I forgot last class. I think I showed you at the beginning, but we didn't discuss it actually. Okay, those are the topics that we are going to cover in class. Okay, so you will have them here. So these 2 weeks, I'm going to be teaching these 2 weeks. Okay, can you read? Is it big enough for you to read there? Okay. So I'm going to be teaching these 2 weeks, and I'm just going to give you an overview of field processing, what kind of processes we have there. And also I'm going to go more in detail into the separation part, okay? The core of the whole process that feeds everything else, which is what we call oil and gas processing, separation, and stabilization, okay? Then, and I'm going to tell you, we're going to look at some tools. Hopefully, let's see if I go that far today, but how do we calculate that, actually? How do we deal with these separation trains? And then Mariana, she was also going to come today, so you can get to meet her. Okay, she will be teaching for the next 3 weeks. And she's going to tell you all about the mechanics, okay? The thermodynamics, the fluid behavior, that part I will try to cover. Then she will pick up on that. We really don't use much hand calculations, okay? We have now computers, we have a lot of programs, software that we can use. So for that, she's going to use mainly HYSYS, and then she's going to go on the mechanics. Okay, for separation, you not only have the thermodynamics, but there is very important aspect how the two phases separate. Okay, so she's going to go into that part, oil and gas separation, and then oil and water separation. You saw that is a very important block in our diagram. And then I'm going to come back and I'm going to talk about water. Okay, water and mainly the relationship with gas. Okay, typically we have some water that comes associated with the gas. We're going to see in the future why. So we have to make dehydration. We have to be able how to calculate how much water we have and how do we remove it. We don't want, remember, we want to separate and then keep liquids on one side and gas on one side. We don't want to have any small liquid in that gas or any small gas in that liquid. Okay, we want to remove. Then comes, so this part, let me just point it here. This will be Milan. Okay, here we have Mariana. Okay, then I will come back again, Milan. Okay, and this big block that's going to be taught is going to be by Harald, okay, Asheim is going to be teaching that part, and these are to analyze more in detail in a component system, okay, and these are really generic things that you can use for different things, but all of his examples will be focused on processing, oil and gas processing. And then we have, okay, here Mariana will teach this section on pumping. And then you have compressor, that will be Harald. Okay. So just to give you an overview, and if you want to get be step ahead and just try to review some material before the lectures, you know more or less what topics are going to be covered. Okay. So now we go back to what we were doing. Okay. Basically, I gave you the rules of the game. Okay. Who is going to teach? When are we teaching? How is the evaluation going? We have these guest lectures. They are on Monday. We start on the 21st, and they will be 1 hour. Okay, they will be there in the petroleum department. And they stop, I think that's just before Easter. And I really recommend if you can attend. They're not mandatory. There won't be any questions for the exam from these lectures. But just to give you the taste that you can connect things that I show here, maybe a simple sketch, and then you go and connect with problems that the industry has. Okay, so I think that part, to make that connection and to be able to connect the thinking, the modeling, the studying, the understanding with the physical system, how it looks like, I think that part is very important. It's a jump that all of us have to make when we go to the industry. No, but if you make it beforehand, it's a bit easier. You already know how a separator looks like. You already know what kind of problems they have. You know already parts of the platform. So I think that part is very important. Evaluation, we have a final exam. We have the date. I think it's 3 or 4 hours. I don't remember. It's going to be written. And you have to, there will be some mandatory exercise, no grade, but just to have access, to get access to the exam. Okay. On my side, I estimate maybe between 4, maybe a bit more, but around 4. Okay, that you have to deliver. Yeah. So then we were saying that we are going to focus basically on the upstream sector, on the part that is processing. Okay, we have 3 main processes that occur. We have the extraction of fluids, the interface with the formation, the wells. Okay. Then we have a gathering system to take the production of all of these wells, and then we have the processing part. Okay, and we are going to talk about, it has a lot of functions. Okay, but that's the core, that's the main part that we are going to focus on. And this is what you have inside. You have, a lot of different things. And with time progresses, you will see we're going to start to populate what you have in each box. Okay. For now on, I'm going to speak in these 2 weeks about this central box. Okay, it's the first box after all the fluids, oil, gas, water, we said here, sand, comes from the well. You have a big block with a lot of things inside that the main purpose is to separate gas, oil, and water. Okay, and feed the other processes. Yeah, then we said, well, we have different destinations we always have to think when we talk about processing, where are the final products gonna go? Okay, that you have to keep always in mind. So with water, we said we have 2 main destinations. Okay, we can re-inject, we can dispose, can be to bed or to another formation. In oil, we can use a pipeline, or we can transport in tanker, or if you are in land, you can use a truck. And in gas, it's a bit more complex. You have a lot of things we can do with gas. Okay, so I listed here some of and you have to be aware, because the gas that goes for power generation, you take it from a different place in the process. Okay, you don't take it from the same place. Now, before we go into that core, I just wanted to give you, and we were making this figure when we had to stop, okay? But I was telling you, what are the conditions you have in each part of the block, entering and leaving each block, okay? So I suggest we try to populate this before we go to the just looking at that box, okay? And I told you before, it's the water that comes out of the main separation process. That separation process is not 100% perfect, okay? So there will be some oil in that water. And the amounts that we have typically are something between 500 and 1,000, okay? And we gave a definition that, you can review, but it's called ppm, okay? It's the content of oil that I have in that water. And after I have that treatment, the goal, if I want to dispose to sea by regulation here in Norway and in many parts of the world, you have to be below 40 ppm. Okay, so you have to take that from 500 or 1,000, whatever you have, all the way down to 40. Okay, here in Norway, I think the number is around 17, so we are quite good compared to the rest of the world. If you, on the other hand, want to take that water and re-inject into the formation, you don't need such a strict requirements. You need only, and I think that number, take it with a grain of salt, but I think it's around 100 ppm. Okay. Now we come to the oil, okay, which is a bit simpler, and then we go with gas, and that becomes a bit more complicated. Okay, but oil, typically, there will be some water remaining in the oil that I cannot take out. It's very difficult. It will need a long separation time to extract all of that water, so it just comes in. And it's between 1 and 3% in volume percentage. Okay, that means volume of oil divided by the total volume is between 1 and 3. It's very little, but if you are producing a lot of oil, okay, let's say 1,000 barrels per day, then it's a lot of water that you have to remove, okay, that you have to dispose. So after that process, what I send either to a pipe or to a truck, so let's start to write that. So for that, I have to repeat a bit the figure. So let's see, here we have, okay, that's oil, gas, and water. And here we have the oil, here we have the gas, here we have the water. And we already said here, maybe, okay, so that's separation and stabilization. Okay, that's water treatment. Okay, so we said here, how much was it? 500 to 1,000 ppm. Be careful with the units of ppm. Okay, you have to know if it's weight, if it's volume, what is it? Okay, what is it that you're dividing? And they have to be the two same units. And when it comes out of here, I can have two, but mainly basically is 100, or that will be oil in water, and here will be 40. Okay. Now with this oil that comes out of here, then we come, what process do we have after for the oil? You have to do three things. What are those? Dehydration, desalting, the next one, and stabilization, okay? So dehydration, okay, and here I get an oil that basically I told you the first characteristic of the oil that we use in the industry is something that we call API gravity, okay, which is just another way to express just the density of the oil, okay, and that I said can be very low, okay, can be even go to 8 or to 6. There are some fields that have a very all the way to 65. Remember the formula. What was API equal to 141.5 divided by gamma specific gravity of the oil minus 131. Is that correct? Yeah. Okay. So if the density, and that's a homework you have, okay, to make with Marcus next time. Maybe the first session will be next week, right? Okay, so that's an exercise you have to make, okay, that I just tell you, you have to plot, okay, API versus either density of the oil. So why do we put the bar on top of the oil, if you remember? I measure it at a particular set of conditions, right? Something that we call standard conditions, which are this oil is measured at pressure 1.01325. If I wake you up in the middle of the night and I ask you standard condition pressure, you have to be able to answer. Otherwise, you're out of the game, okay? I wake you up in the middle of the night and 15.56. So I just want to make a plot to see how it looks like, okay? And make it in the range, something between 600 and 1,000, okay? Or 1,100, 1,100. And these units are the kilogram per cubic meter, and you see how the function looks like, okay? But you will see something very important is that API is not linear. It's something that tells me if you have a very low number, okay? If I have a number close to 8 or close to 10, it tells me that the density of that fluid is very high, okay? Similar to water. And those type of oil, usually they have a lot of heavy components, okay? We're going to see now oil is made out of very different things, okay? But when it's very heavy, that means it has a lot of things I'm not very happy to process, okay? It has a lot of things that is going to take a lot of effort. If, on the other hand, I'm on the other extreme, okay, 65, what does it mean? The density of the oil, right? If this is high, that means that this is low, okay? Because they are inversely proportional, okay? So that means that if I have a very low specific gravity, my density is low, and that's something very good. Okay, I can always take that oil and put it on the car, okay, and just run with no effort, with an oil at 65. Okay, so, but just make a plot and just not to spoil any surprises, okay, but you should get something like, after all, it's like an inverse multiplier, okay, so you should get something, a trend like that. And that's something useful because it's not linear. If you say a crude of 600 is very good, and you look at a crude of 900, is very poor. So it's not linear, the scale. You cannot say that it becomes better linearly with the scale. Okay, you just have to use this strange scale to reflect that. And that's why we use this API. Even though it seems strange, you say why it's crazy, why petroleum engineers are using that. That's the reason. Okay, it has some logic into it. So again, I tend to clutter so just, I'm going to put it down, okay, otherwise I won't have space. But just that's one homework that you're going to have with Marcus. And here also, it will help you to practice your plotting skills, okay? When you're making a plot, you're not making for yourself, okay? It's not that you will go back to the plot in 20 years and look at it and say, oh, I was such a good student, okay? It's going to show it to other people. Or the other people are going to do something with your results, okay? So you have to have that in mind. Maybe you understand you have very good eyesight. You put the letter number 8. You show it to me. I'm starting to be old, okay? So I need a bigger size, maybe 18, 14. So you have to take all of that into account, that the plot should communicate in a proper way what you are presenting, the data that you're presenting, okay? Some of the recommendations that we have are you have to use the axis. They have to be in black, okay? So they have to be visible, okay? I recommend to use outer tick marks, okay? That means these small ticks that you have here, such that you know where the number is. Okay, if the number for some reason is very big, you have issues saying exactly where in the axis is. Then the font size, you have to decide, depends on computer from computer. But I think a number between maybe 14 and 18, something that works more or less. Okay, a big number. Also try to use bold when possible. That you're going to present it and you want to see, that it will be easy to read. The axis titles, okay, you have to have first the name of the variable, then you have to put the symbol, okay, that I use. For example, here I will put oil density, comma, raw oil, comma, and finally you put the unit that I'm using. Yeah, anything else? Okay, and also there are a good number of significant digits, okay? If I tell you I have a density of 600 or 800, it doesn't matter much if it's 600.01325. It doesn't matter. 600, 800. So don't use all of those numbers if they don't mean anything. Okay, if you're telling me a number that has 0.01 and another number that is 0.02, here it matters. Maybe it matters to have one extra decimal point. Okay? So these are just some guidance and that you have to take into account when delivering the exercise. The last one was number of significant digits. Okay. Okay, so API, which is just density, simply density, is supposed to be between 8 and 65. The water content, why water was important? If you remember from last class. One main enemy, okay? That I wake you up in the middle of the night. Why water is important in oil transport? You have to tell me, okay? Corrosion. That is one big problem. Corrosion in tanks, corrosion in the tanker, corrosion in pipe, all kind of things. So here the water in oil, I can have some cases where it goes down to 0.5. It should be below 0.5. Or can go all the way to 1%. Okay, that's typically in Norway. Platforms, they produce oil, which is, they call it like wet oil. Okay, it has some water. Sorry, typically it's between 0.5 and 1, but in Norway people produce up to 2%. Okay, but typically all around the world is between 0.5 and 1%. So you see the reduction I have to make. You will say, well, it's not very much. Here, remember, I had from 1 to 3%, okay, in volume. And here I have to reduce to 0.5. But it really takes, you will see in the lectures of Mariana, it takes a lot of effort to bring that number down, just that 0.5%. Okay. If I'm saying transport in a tanker, okay, if this goes to a tanker or a truck, okay, I have to have the pressure that I call Reid vapor pressure. Okay, this stands for Reid vapor pressure. Should be below 11 psi A. Okay, and that, in a simple way, we are going to go. We have to talk about phase behavior. Okay, we have to talk about different things to see what is this vapor that you're saying. But basically, if I lower to 11, that's the point where some still gas comes out of the oil. Okay, it still has some vaporization of gas. Think about it. It's not exactly that, but think about it in that way. Okay, I want that if I transport in a tanker or truck, I have to go down to 11 psi, which you see is less than the ambient pressure. How much was ambient pressure? 14.7, remember? So to get some vaporization, okay? And Reid, it's just the name of the measurement tool is used, okay? Then we have, if it's on a pipeline, is actually much better, okay? I don't need to be so strict because I'm containing any gas that for any reason vaporize, I'm contained on the pipe. So I have to be a bit less conservative. So PSIA, RVP, okay, or 150 TVP, and TVP stands for true vapor pressure. okay? Which is, they are related, okay? It's just the way you measure it, but they are related. This true vapor pressure and real pressure is related. That's the one we use in Norway. Most of the fields we use, okay, 150 TVP. Okay, now another thing, there are two more things, and then we have to go to the gas, okay? One more thing is the salt content, okay, the amount of salt. And the salt has to be between a number 10 and 30 ppb, okay? And ppb stands for pounds per thousand barrels, okay? That's the acceptable number for corrosion, accumulation of solids, all kind of thing. That's the number I'm aiming for. And then, very important, the H2S. Okay? Have you heard about H2S before? Any of you? Yes? What did they tell you about H2S? They have to tell you, the only thing you have to know, you have to run away if you see H2S, okay? If you see a detector, H2S, you run away. It kills you very quickly. Okay, but also because of safety, other things, we want to keep the concentration of H2S between 10 and 100 ppm in weight. Okay, just because of safety, can also do some ugly things with corrosion, so we want to keep limited to that. So if I have a field where I'm producing with high H2S, which they are, okay, especially in the Middle East, I have to do something extra to remove that H2S. Okay, I have to do something. Here in the North Sea, we are a bit not spoiled, but we're a bit blessed that we don't have too much H2S. We don't have to care too much. People that have high H2S, they have to deal, is a big problem. Okay, then let's see here. I will bring it down a bit. Okay, now comes the gas, and here you're going to hate me, but don't do it just yet. Okay. What was the next step for gas after I separate? Remember, for the exam, you have to know it. You know, I wake you up middle of the night, you have to answer. Hydration, right? Okay. Why? We don't want any water coming out of solution from the gas. Okay. We don't remember liquids, something that we don't want. Okay. After that, we have, what do we have? Compression, right? And here we say it can go to power generation, gas lift injection, EOR injection, all kind of injection, okay? And here we have a line, and that's where we say, you know, what kind of specifications we require here, okay? What kind of things we require on this tree. So first, the pressure is something between 100 and 200 bar G, okay? Remember we talked the difference between relative pressure and absolute pressure. It's just the reference point that you use. Okay, here comes something interesting. Water dew point, okay, is minus 18 degrees Celsius, okay, at 69 bar G. It means that to start getting water out of this gas, I have to go down to minus 18 degrees, exactly at 69 bar. It's a strange number, I know, but we are going to go later to phase envelope, and you're going to see what that means, okay? But basically, that I can have no water should condense down to minus 18. And I have my drying process has to make sure of that, has to reduce the water content until I get no water. And that typically means a water in gas content of should be less than 4 pounds per million standard cubic feet, which is very low. Okay. So just before we continue, how many of you are familiar with standard conditions rates? How many of you? Not much. Okay. It's just a rate unit. Okay. It's like yeah. So let's make a small detour. Okay. I think there will be a few detours in this class. Okay, so the next comment comes on, it's a short comment on, in petroleum engineering, we use standard, what we call standard condition rate. In petroleum engineering, we use standard condition volumetric rate. So let's say that you're, okay, we have a master student, okay, not you, someone else, and he's sitting just next to a pipe. Okay, it's a very boring job, sitting next to a pipe. And we have to put a helmet due to safety. Okay. So they ask this guy, okay, the manager, he's asking how much mass or how much is circulating through that pipe. Okay. And depending on the background of that guy, he's going to give you different answers. Okay. Any of you mechanical engineer? You? What will you say if they ask you how much fluid is circulating through this pipe? You have to measure, but what number do you give? Which units do you use? That's a density, but if you want to say how much is passing through that pipe, you have to use a time unit, right? So it's kilogram, either per second, day, whatever. Okay, perfect. Any questions so far? Everybody understand the mechanical engineer, right? But anyhow, he's in an oil field, he's fired. Okay, then bring another engineer. This guy is a mechanical engineer, chemical engineer. He thinks he's smarter. Okay, so they ask him again, how much fluid is circulating through the pipe? What is he gonna say? What chemical engineers, what do they like? This thing called moles, right? Moles, okay, so this guy is going to say moles per second, okay? And that's correct, that's very correct, but he's also going to get fired from the field, okay? Then comes the petroleum engineer, and what is he gonna say? He's going to use these crazy units, okay? So if we are in field units, we use for oil, okay? We use standard barrel per day, okay? And for gas, we use standard cubic feet per day. These are what we call field units. Okay, and if I say in SI units, actually the units are the same. It's in standard cubic meter per day and standard cubic meter per day. But the S is extremely important. Okay, you have to always, if you are referring, if you want to say how much is circulating through the pipe, you have to remember this S. It's extremely important. Okay. Okay, so all of you know cubic meter. That's just volume unit, right, per day. And barrel is just a barrel of oil. How much is a barrel of oil? How many liters? No? How much? Okay. Well, if I wake you up, no, that you won't get that's okay. But the thing is that, okay, a barrel, these are units of volume, okay? Cubic feet also you can visualize. A cubic feet, you put a feet in 3 dimensions, that's a cubic feet, okay? But what is very important is the S, okay? If we say, and we're going to see now, if it's a volume without any S, okay, just simply cubic meter, okay? The volume depends, if the fluid is compressible, it will depend on the pressure, okay, and the conditions of pressure and temperature. So by putting the S, I'm saying that this is volume measured at standard conditions, okay, SC, at PSC 1.01325 bar, okay, and TSC 15.56 degrees Celsius. Their mesh is okay, it's volume, we agree, but it's not going to change because I measured always at the same pressure and temperature conditions, okay? So this guy is not free to say, well, at this pressure of the pipe, okay, at whatever pressure I have here, he's also going to get fired. He has to say, well, what is circulating there are 100 barrels. If for some reason I take that fluid to those pressure and temperature conditions. It's crazy, okay? It sounds crazy, but that's the way we work. It's like you'd remove that. Let me just make a bit more space. Okay, we take that block, okay, of oil that I have here. Actually, I have take the whole block, might have oil or gas, okay, and I take it to standard conditions, exactly at PSC and TSC. Okay, and there I count how many barrels I have. Okay, and there I count how many barrels or how many standard cubic meter I have. Just, but just if you still don't get it, no, that's okay, that's normal, but be aware that that's equivalent of a mass flow or of a molar flow. That shouldn't change. If I put the engineer here, or I put the engineer here, or I put the engineer here, and I have a steady state, I have no accumulation, it's always the same, they should give me the same number. Okay, the 3 engineers, no matter in which position of the system I see. Okay, so that's long explanation, but just to say here we need 4 pounds per this unit of rate. Okay, I could use kilogram, but petroleum engineer like, because that you multiply directly by price. Okay, you know how many dollars per barrel you get, so you can get already how profitable the well is, okay, or the gas. But if you use kilogram, the manager cannot calculate, so you are fired. Okay. Then we have another thing that we have to take is CO2. Okay, CO2 has to be less than 2.5 mole percent. Okay, because of different reasons, but mainly also this corrosion. Okay, to avoid corrosion. H2S, because of safety and corrosion, the same thing, has to be less than 5 ppm. And here, I'm going to throw an ugly name at you, okay? But we just, so the Crickondent term, Crickondent bar, has to be less than 105 bar G, and the Crickondent term has to be less than 40 C. How many of you know this word? Crickondent term, Crickondent bar? Nobody? Okay. So just keep it in mind, that's, we're going to see very soon, okay, what does it mean? But just, it's related to the first point here, okay? That you go down in pressure, down in temperature, and you don't get any liquid out, okay? And this is referring to water, but this one is referring to condensate, okay, to oil. Okay, then I have Okay, now I finished more or less. Those are all requirements that I have. Now comes what is the next step? Okay, here I have gas conditioning. Okay, that's called dew point control. What else do I have? I have NGL extraction and something called fractionation. Okay. Okay, just like to refresh, what up to which point happens typically on a platform? Up to here, okay? Up to here, everything, all of these happen on the platform, okay? From this point on, I have a pipe that takes the production of gas from the field to another plant, and this is typically a plant onshore, an onshore plant. They call it Onshore Gas Plant. Okay, and this we call it, even though it's not really wet, okay, it's mostly gas and it's very dry, we call it wet gas pipeline. And that happens onshore. So here we have a split between onshore and offshore. And then we have here another stream in which we have the dew point has to be minus 10 at 50 bar. Okay, which you see is actually lower than what I had before. No, it's not the water dew point. Okay, CO2 and H2S, they are the same. H2S 2.5% and that below 5 ppm. But here there are a few things. You have also a calorific value. Okay, and also it has something called the Wobbe index. Okay, and these are related to how much power energy is released when I burn this gas. Okay, if I have a gas for some reason it releases just too much energy. Okay, that energy, if let's say I have a power plant, okay, is going to increase the temperature of the burner. Okay, and the burner is made of a material that only tolerates up to certain temperature. If I put a gas which burns and gives a lot of energy, you will think, oh, that's amazing, I want more of that gas. But the temperature will increase and then it will cause damage on my power plant, okay, generation plant. So that's why I have to be sure, and these two are related to that, okay? Let's call it here burning gas energy. They are related to keep it below. It should be above a number, but it should be below a number such that I don't have, safety issues. Okay? And we will see now that's controlled with all of these, heavy components. Okay, but that's more or less the picture. You see, in water, really, I just care about the oil content, not much. Okay, oil, I start to worry about some other things like salt, H2S. Okay, but it's a few things. But when I go to gas, I have to be really, really careful. Okay, and that's why gas, I have so many things to process that gas. I have to be sure no liquids come out. I have to be sure no water comes out. I have to be sure these two guys are below a number. I have to be sure that the power. So a few things I have to, be careful. Clear so far? Yep. Now, should we take a break or five? Yes. What do you say? 5 or 10-minute break? Yeah, let's say 10. Okay, 10-minute break. Okay, we come back 3:10. Continue. So, one thing is, what we call, sometimes we say product specifications, okay, or product specs, or assay specs. When we talk about oil, we're talking about all of these characteristics, okay? If you go to, you can have one crude assay. Okay, here you have one which is called Arabian Light. Okay, comes from Saudi Arabia, and it has the API, sulfur, water content. This is related to this true vapor pressure. Okay, read point, density, par point, viscosity, a few other things. Okay, but basically those are the specs. The specs that that crude has, that's like the product specs. Okay, and also for the gas. If I'm selling this gas to a pipeline, that's mainly when it goes to a pipeline. Okay. I was told that I have to improve a bit my handwriting, so I will do my best. Okay. Those are also the numbers that we have to be careful. Okay, all of these factors. That's something that if you don't meet that, if Statoil comes and they have this gas, they want to sell it to Europe, but one of the numbers is not within the range, they're not going to buy it. Okay, they have to do something with that gas. They have to do back or so. That's why it's so important that you meet the product specs. Okay, and there might be some refineries, some countries that they accept, you know, with different specs, okay, with different API, with different H2S, but so we have to be very careful with that. Now let's talk about that heart, okay, that center, which is the oil and gas separation and stabilization, how that process looks like, okay, and there are basically two functions of that. There are many other functions, okay, but there are two main functions that that process has. One of them is to mechanically or physically separate oil and from gas and from water. The other reason, okay, is to basically to deliver stable oil and gas, okay, so in a way it's like repeating, okay, stabilize oil and gas such that if I lower even more the pressure, then I don't have significant amount of gas coming out of the oil, and I don't have significant amounts of liquid dropping out of the gas. Okay, but also one main thing here is that I want to, typically what I try to do, I try to increase is the ratio between oil and gas. Okay, why? When it becomes higher, I get more oil. Okay, and oil is something that I can sell much, you know, with more is much more expensive. Okay, oil. So in our benefit, I try to always try to increase the ratio between oil and gas. Okay, I try to get more oil out of it. And we're going to see a bit how that's done. If if we try to make the whole process like a house, okay, that sometimes we make it, just to summarize, we put, that's the field stream, okay, field stream. Okay, and we have this house, something happens inside, okay, a bunch of processes, separation, I have pumps, etc. And at the end, I get two streams, okay, I get the gas and I get this oil. Okay, and I get, remember to know how much we're getting, we use this standard conditions rate, okay, Q gas and Q oil. So I have a parameter called GOR, okay, it stands for gas oil ratio. That I use is simply GOR is simply Q gas divided by Q oil. And one of the goals of this separation process is to bring GOR down, okay, to have less gas. So to bring GOR down. So how the process looks like. And you have to be able, again, if I ask you to sketch this, I wake you up, you have to be able to do it, okay? So what it has, I have here the inlet stream, okay, or well stream. And what I have typically, I might have a valve, okay, but not sometimes I don't have, okay? And then I have a vessel, which is a cylindrical, typically a cylindrical vessel, where I separate the mixture, okay? And you will see now a picture is simply a cylinder where I have a level, okay? I have a level here where I have the liquid and I have the gas on top. After that, okay, and that's what we call the first one that the stream meets after it comes from the field is called the high pressure, okay, sometimes abbreviated HP separator, okay. And these separators sometimes we call simply gravity separator. Okay, simply by gravity they have different densities, the oil and the gas they separate. After that I get this oil, okay. Sometimes I have a pump or not, it might be. Then I take it to a valve just to drop the pressure, okay. Then I take it sometimes to a cooler, okay. And then finally I enter the second stage, okay, which is the medium high pressure, that is the first stage, that is the second stage. Let me maybe put it here. Or EMP, which stands for medium pressure. And I have again the same arrangement. I have a cylinder with liquid and gas. And I can repeat that as many times as I want, okay? You will see when you have the class about HYSYS with Mariana, you're going to have an exercise on that to define how many stages. And we are going to see now what that does, okay? But typically in the North Sea, in Norway, we have something between 2 and 4, okay? It's more common 3, okay? But it's something between 2 and 4 stages. Okay, in NCS, that stands for the Norwegian Continental Shelf. Okay. After that, I take again, we are following just the liquid, what the liquid is doing. Let's make 3 stages only. Remember, sometimes I might need to have a pump just to flow. If the separators are far away on the platform, I might need a pump, but we don't have it just now. And then we have this separator, that's the most typical configuration, where I have high pressure, medium pressure, and the last one will be low pressure. Okay, very simple, low pressure. The third stage, or LP separator. After that, this liquid, I go and I put it on a tank, if my platform has a tank. Okay, it's not the same house than before, where I simply store it, and I might still have some gas coming out of here. I might have some gas coming from the top, but it's going to be relatively very, very small. Okay, and here I have the Q of the oil that I'm producing. Okay, and that tank, the pressure, it's simply atmospheric pressure. Okay, that tank. So you can really see now where this Q oil is measured. Okay, you see, you go all the way after all the separation stages after the tank, and you measure how much rate you have there. And that's simply the rate, this standard condition rate that you're producing. Actually, that's the number people measure to, to calculate the revenue of the field. Okay, now let's follow the gas. Okay, with the gas always it's a bit more complicated. Okay, just let me show you a figure, how, I think I have a figure, how that looks like, or a photo. Okay, that's how these separators look like. Okay, Mariana, she's probably going to show you a bunch of pictures, okay? But you have here is simply a cylinder, okay, with two covers on the side. And inside, it's not simply just empty, but you might have, you have another figure here. Okay? Inside, you have a lot of elements, okay? But separation happens due to gravity. Okay, so all of these elements that you have, it might seem complex, but it's just to help separation from the liquid and from the oils from the gas and gas from the liquid. Okay. Now on the gas, okay, what we have here a line, okay, that goes to dehydration. Okay. Okay, we have a line that goes to dehydration. And typically that line, the pressure is actually higher if we call here P1, T1, okay, let's call it like that. Pressure 1, pressure 2, temperature 2, pressure 3, temperature 3, and here we say P standard conditions, T standard conditions. Okay, so that pressure that I have here, which is the pressure entering dehydration, is typically higher than P1, okay? That pressure is higher than P1. Therefore, I have to take that stream and put it through what increased pressure of the gas? What equipment do I normally have? People say like a pump, but for gas, right? How do we call a pump for gas? A compressor, okay? How do we draw a compressor? Okay, they teach it in kindergarten, I think, okay? You have to use a big side where you have, remember, always the big one is the one that takes the most volume, okay, where the pressure is lower. Then you compress, and then you obtain smaller volume. So that helps you to remember why, from which side you put the. But it's not so simple, okay? Why? Because the moment this liquid flows into the pipe to go to the compressor, the pressure is going to reduce, is going to drop, okay? Because it's losing energy when it goes to that compressor. When it drops, you get oil out of this gas, okay? And you can get water, you can get liquids out of this gas. And compressor doesn't like liquid, okay, at all. So how do we solve this problem? First, the way it is solved, okay, so that I don't put the compressor right away, but I put a cooler, okay, such that I try to even make it cooler, and I try even so much more liquid will drop out, okay? So just to be sure that at the inlet of the compressor, I have no liquids, okay? So here we'll have a high amount of liquids, okay? Then I come to it's like a small cylinder, okay? It's like a small separator, but because it's for a high amount of gas and low amount of liquid, I call that a scrubber. Okay, but it's very similar to this one, okay? But because it's for gas, it's vertical and it's much smaller. But the main purpose is to remove that additional liquid from the gas. And after I do that, okay, I can be sure that whatever is coming into that compressor is relatively dry, no liquid. Okay, so I cool down to remove even more liquid, soak out of that liquid, and then I simply connect it here. Okay, but we forgot something, right? There is something that is not working in our diagram. What is it? That liquid, right? We left some liquid stranded there. It's crying. It doesn't have anywhere to go. So where do we put it? Back in the separator. But to avoid having a pump, sometimes what I use is I just come here and I just inject it right there. Okay. because the pressure will be lower than P1, but still will be higher usually than P2. So to avoid having a pump and then to inject it to the same separator, I just send it to the next separator. Okay. Now let's do for the other two. Okay. Good thing we didn't choose to paint 4. Okay. But for the other, we have again a cooler, exactly the same arrangement. We have a scrubber. Okay. And we have a compressor. And let's put that liquid. That liquid now, following the same logic, comes here. Okay. So where is that gas gonna go? Okay, that gas I could just send it directly straight here, right to that line. Let's maybe prolong that line. Okay, and I'm going to put that line that goes all the way here, and that dehydration. Okay, the thing is that compressor, it's a component that uses a lot of power. Okay, and the power is, in principle, is driven by the difference in pressure between inlet and outlet. Okay, so even though here the rate might be very low, okay, but it's very small. In every stage, the gas that I take becomes smaller and smaller. Okay, typically, but here the delta P is higher because here I have to go from P2 all the way to P1, to P dehydration. So to avoid that high power requirement, what I do, I just send it to the compressor of the first stage. Okay, and I typically, here I have no space, so typically I send it just before the cooler. Okay, so I have the cooler here, and I just put it there. Okay, such that I do the compression like in steps, in smaller delta P steps, and such that I don't have to invest so much power to go straight from here to here. Okay, I do it with a small compressor with small delta P, and then I use this big compressor that will take a higher rate and then a smaller delta P. And then we have the last one, which is here we have this gas, and we do exactly the same thing. Okay, then I have here a scrubber. Okay, and then I have the gas. I have another compressor, and that doesn't go directly, but goes actually, we can send it straight to the previous. There are some different arrangement, or sometimes what I do, I just send it here. Okay, we're going to see right away how it looks like in real life, but just to, so you have to be able to sketch it, okay? Even though it's very general, doesn't have all components, there are some things that are not exactly correct. You have to be able to know it's simple, a sequence of separators, and you take the oil from one to another, and you take the gas from one also to another, okay, on the way back. Okay, on that liquid, I typically here I have no choice, but I have to put sometimes a pump, and then I have to bring it here. Okay, again, back to the first stage, to the third stage. Okay, so let's see now how that looks like. Okay, we're going to see two things that are actually here, offshore turbine. But there are two, be careful. Take one of each. you have it. So I'm going to put some material on the, I think I will put it on Blackboard, okay, about engineering diagrams. You're going to be exposed when you graduate to a bunch of engineering diagrams, okay? To understand the process, they're going to be exposed to a few things. So I suggest to get a bit familiar what kind of things you can expect. Okay, I'm going to put this is from a book, okay? Here is the name of the book. You can find it here in the library. And it's very short, just 7 pages, but it shows you the type of diagrams that you have. So that's the one we have used so far, just a block diagram. You try to summarize in a very rough manner where goes each fluid. Then you have what is called a process and flow diagram, okay, PFD. That is what you have in your hands, okay, what I have also tried to draw. And you have other things, pressure and instrumentation diagram, you have isometric. So I just recommend you to read. It's very short, but you just get an idea what kind of diagrams we use in petroleum. Okay, I'm going to put that on Blackboard. So let's look at what you have now. And okay, let's go first to the one Christine. Okay, both of them are just offshore here from Trondheim on this area. But let's go to that one first and let's try to identify if we see all the elements that I was discussing here, that I was discussing before. Okay, so first you have to find the inlet. Okay, so that's very simple. You see here to the left, the wells. Okay, Christine wells. Then you go and what you should meet initially, the first thing, you meet the first stage, okay? And here you see you have one for water. Water separation typically happens on the first stage, okay? They remove most of the water. We took out that because Mariana, she will show you exactly how do you, just look at the gas and the oil, okay? So now let's follow that oil, okay? So oil goes from the first stage, it has a valve, it has a cooler, and then goes to the second stage. And you can see the numbers, okay? 87 bar, 121, quite hot, okay? Then goes to the second stage, again, more separation. Then I have the third stage, okay? And then in this case, I don't have a tank, but I just simply goes to another platform, okay? Osgard C. Now let's see the gas, okay? What happened with the gas? So the gas comes out of the first stage, okay? Then it goes to the cooler. That's a cooler, okay? I don't know if it has a, but that's a cooler. And the arrow indicates I can regulate, okay, the temperature. A cooler, then I have a scrubber, and then I go into this dehydration process, okay? In this case, I don't need to have, maybe I don't need a compressor here. I think so, because the pressure is quite high. So I don't need to have this compressor. It just can go at that pressure straight to, yeah, it goes straight to the dehydration. Don't pay attention to the rest, okay? We haven't talked about that yet. But just look, you have to identify the first, the separation stages, and you have to identify, the oil and the gas lines. Then on the second stage, you see here it comes cooler, scrubber, and then it goes to a compressor that goes back to the gas of the first stage, where you have a cooler, a scrubber, and then goes up. Okay, so exactly the same thing we have drawn by hand, but just a bit more complicated. And the one on the third stage goes cooler, scrubber, compressor, and then goes to the compressor goes cooler, scrubber, compressor, and then goes to the second stage. Okay, I don't know why they have this here for some reason. Okay, but in a very simple way, that's what we have, that's what we draw here in class. Yeah, and also note that the liquid is not being injected on the on the following stage, but they use this pump to inject it on the same stage. That clear? Yeah. Difficult to read? No, right? Not much. Sorry. Okay, just to see and then see, but the gas, you have to be careful. I cannot just merge it. I have a compressor, so I have to take out the liquid and put it in the compressor. So now let's look at the second one. That was hydrogen. Christine is a gas field, and hydrogen is an oil field. Okay, and that is a bit more complex. But exactly the same thing. You start by looking at the same. Okay, first let's see where is the oil coming from. Okay, you see here from typical. Yeah, don't mind, it's TLP, stands for a type of platform called tension leg platform. Then you have the choke, you have a manifold, and then you have the first stage separator, okay, which is here. Then you see you have also water separation. Then the liquid goes to the second stage. You have a valve, and then you have a cooler, in this case a heater. Then you have the second stage. Then comes out of the second stage, you have a valve, and then it goes on the third stage. Okay? And after that goes to metering and to storage. Don't mind about, you will see the construction, but basically I can drain oil from the sides also, okay? I don't have just one draining point at the end, but the liquid is coming through the center and then goes through the sides and draining on the side. Okay, that depends, you will see on separator design, but for now don't mind, okay? That is like if you had one line. Okay, and then on the gas, let's follow the gas for a moment. You have gas, then goes to a scrubber, goes to a cooler, then goes to a scrubber, and then a compressor. Okay, and here you have the dehydration part, okay? And the liquid goes, you see here they don't use a pump, so they send it straight to the second stage, okay? Then the gas from the second stage goes to a cooler, then a scrubber, then a compressor, and then it goes to the scrubber of the first stage, okay? And so forth. Okay, so exactly with a bit more complex, and you see more diagrams. They will be maybe a bit scary at first, but you have to be able to locate and identify this equipment. Okay, after you identify the equipment, you identify where the oil and gas are coming from, then things get much easier. Okay. Another thing I wanted to say, it's be careful. You might have, so that's what they call the three separators. That's what I call sometimes the processing train. Okay, that's what I call a processing train. Okay, sometimes if the fluid is too high, let's say I have a huge rate of oil and gas. Okay, I need more than one train. Okay, if I put one big train, it will be maybe too big, difficult to manufacture, costly to manufacture, costly to install, costly to move. So I prefer to put just simply two trains, okay, two trains parallel to each other. That you can see in some things. Yeah. So okay. Any question? Okay, you're going to look just at the separation here, and after you're going to understand the rest, okay? We're going to talk about dehydration later, and Mariana, she will talk about how separation actually takes place, the mechanics, and the water treatment, okay? So don't be scared if you don't understand anything. Oh, here interesting to see the destinations of the gas, okay? Where is gas going to? So you have, you see gas injection well that goes to the reservoir, okay? It can go to gas lift, okay? It can go to export. This is gas that I'm actually selling for, heating or for power generation. That also goes to gas export. Gas lift on the riser. So I use all of these others for things on the platform, and then I export basically this one and this one. Okay. 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 Now let's see how we should be able to how do we study, okay, or what tools we use to study these processes, okay? Yeah, before that, I know I was missing something, and it's this, okay? So let's do it like that. How do we study okay? We have to look at two things, okay? We have to look at, of course, we need thermodynamics, okay, and here we say is a mixture, okay? We're going to see now oil is made out of many different components, which are not pure, okay, which are a mixture. So we have to look at thermodynamics of mixtures, okay? And we call it typically hydrocarbon mixtures, HC, hydrocarbon. Okay. And we also call it, sometimes we call it is either fluid behavior, okay, or we call it phase behavior, okay, or we call it PVT, okay, behavior. Okay, PVT stands for pressure, volume, and temperature. Okay, so those are like or is how we call the scientific area, okay, that we need for analyzing that. So what are the components that oil and gas, so oil and gas are made, consist of um, of several components, right? What we call pure components. Okay, what components do we have in oil and gas? First, we have something that we call non-hydrocarbons, okay, where the most important are CO2, nitrogen, okay, and we have H2S. Okay, these are the non-hydrocarbon. We have other things also, but those are the ones that take most of the space, okay, in oil and gas. Then we have all the what we call the hydrocarbons, okay. And here, what do we have that you learn in primary school? We have all of these guys, right? Methane. How does methane looks like? Okay, you saw we have a C, only one C, right? And we have covalent bonds, and it has 4 H. Okay, right? you have that in your, okay, methane. Then we have, we sometimes like to, abbreviate. We just say C1, okay? Methane C1, C2, C3, 4. And when we increase the number of carbons, something happens, right? What happens when you increase the number of carbons? That, for example, C4, right? You could have like that, okay, with H here. But also you have what is something called isomers start to come out, right? Where each atom can be arranged in a different manner, okay, but still having the same chemical formula. The chemical formula here is CH4, okay, and here is also C4H, if you remember, 10, right? Okay, you don't have to count. What is the formula for alkanes? Those are basically alkanes, what we have. The formula is CnH2n+2, right? Okay, it's back. It's not going to go away. So, okay, then you have what is called an isomer, okay? Okay, that we in this case call IC4, isobutane, okay? Isobutane. Okay, and then we see C, 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 and then we have C here. And we keep exactly the same chemical formula, okay, but we have a different compound, okay, that might have slightly different properties than simply butane, okay, what we call normal butane. So here we have IC4, we have C5, IC5, and when it comes to 6 and above, it becomes very difficult to track all of these isomers. They might have infinite number of isomers, okay? So I sometimes try to group all of them under the same compound, okay? C7, C8, okay? And I have more, maybe all the way to, depending on the crude, C35, C50, okay? I have, let me just move it a bit up. Okay, I can have all the way to maybe C50 or C35, okay, to a very high number. So, yeah, something just to clarify. Maybe I can make some space here. Okay, when we talk about NGL, okay, natural gas liquids, we're saying components that are typically on this range. Okay, that's what we call NGL. When we talk about LPG, liquefied petroleum gas, we say is typically these two guys, that's LPG. And LNG is typically maybe these two guys, LNG. Okay, so you understand what's the difference. Okay, NGL covers a higher number of type of components, and it can vary very much. LPG is basically what we use to make barbecue grilling, in summer, what we have in these containers. And LNG, we're not covering here in this class, but basically we take methane, almost pure methane, we compress it, we lower the temperature, and we make it into liquid, okay? Liquefied natural gas. Okay, so if we have all of these components in the crude, okay, how do we know? And each crude will be different, okay? Each well, each reservoir will have it will be made of different proportions of this component, okay? Maybe one field will have a lot of methane, one field will have a lot of C6, one field will have a lot of C7. So how do we characterize, the hydrocarbon mixture? The the oil and gas are characterized by its molecular composition, okay? And the molecular composition, I just say, okay, I just use mole fraction. A mole fraction I use for the mixture, I use the letter Z, okay, and I use I just to define that is the mole fraction of that component, okay. And Zi is just defined by the number of moles of pure component I, okay, divided by the total number of moles. Okay. That means that my hydrocarbon, I typically have, for example, let's say here Zi. Okay, let's say I have only 3 components, okay, C1, C3, and C8, okay, and this will be 0.4, this will be, I don't know, 0.3, and this will be 0.3, okay. That means that that particular fluid, I'm not sure yet if it's oil or gas, okay, but that particular fluid is made up of 40% mole fraction, be careful, you have to see the units, mole fraction of methane, 30% mole fraction of propane, and 30% mole fraction of octane. Okay? That's the molar composition of that fluid. And that's the way, that's like its name, okay? We don't need anything else. That's everything that gives me information about that fluid. Okay, and that's the most important, really, the most important information I need to start, trying to find out more information about that fluid. Okay, we have also another fraction. Mechanical engineers, we like it very much. How do we call it? Mass fraction, right? And mass fraction is simply, I use the letter W, I, and it's simply the mass, total mass of component I, okay, divided by the total mass. Total mass that I have. And that's also something I can use to characterize my yeah. So what's the conversion between the two of them? Mass fraction and mole fraction, if you remember. We have something that we call a molecular weight, right? The molecular weight of a pure component, okay, is simply the number of moles divided by, the number of the mass divided by the number of moles. Of that particular component, okay? So if you remember, how much is it for methane? You don't be mad with chemistry, okay? It's going to help us a lot in this. Okay, you just have to have some tolerance for some chemistry, and then you're going, But don't be mad. Don't look it with with bad memories. We need to use some of these tools. So it's 16, right? Okay, because how do you calculate the molecular weight of methane? You have 1C, the weight is 14, right? And then you have 4H, no, 12, sorry, and 4H, then you have 16. Okay, and that tells you those are the units. Typically in SI system, we use kilogram per kilomole, or we use gram per mole. Okay, so to convert from one Okay, and the molecular weight of the mixture, how do I calculate that? Molecular weight of the mixture. Okay, is the sum of from I equal 1 to the number of components I have, that's number of components, of set I times the molecular weight of I, right? So it's like a weighted sum of each component, the molecular weight of each component times its mole fraction. Okay, if I have more C8, then the mixture will have a molecular weight similar to C8. Okay, if I have more methane, then the molecular weight will be similar to methane. Yeah, so just to, I didn't cover, well, but that happens, right? So what is the relationship between WI and X and ZI? Because you're going to need, sometimes you read the specs of a crude and they come in these two units, okay, mole fraction or mass fraction. So what is the conversion between them? We say that let's say this WI, right, is the mass of component I divided by the total mass. And at the same time, the mass of component I is the number of moles, right, of component I multiplied times its molecular weight, right? Yes? From the definition from above. Number of moles of I times the molecular weight of I. Divided by, okay, total mass, the same thing, okay? The total number of moles, okay? Times the molecular weight of the mixture. Okay, and at the end, these two guys, they divide, so that's the mole fraction, ZI, and here we have MWI divided by MW of the mixture. That correct? Yeah. You have to be careful. I might be making mistakes. Okay, it's late. Getting tired, so you have to be checking the. Okay. So if that's clear, maybe you already knew it from before, it's trivial, but just to be sure we are on the same page and we have a way to say how much. We know oil and gas may have many different components and we have to be able to say how much it has of each, okay? And we might have a bunch of them. To say we have it's like its indicator, it has a name, and that's the way we characterize the mixture, okay, with this mole fraction. If we have that, then we have the first step to start making calculations, how that fluid is going to behave, okay, how much oil, how much water, how much oil and how much gas, how is it going to split, what kind of density is it going to have, what kind of properties is it going to have, okay, so that's the first step we need. Okay, I think that's all I had for today, okay? So to summarize, we said the specs in some positions, right, of these boxes. Then we came into how do we say, the multi-stage separation. That's the core, and it's very simple, simply a bunch of separators. We saw some diagrams, how it looks like. And then we went into how do we characterize that mixture, okay? We need two things, mole fraction or mass fraction. Now the next class we are going to see what tools we use to calculate the splitting, okay? How much for a certain composition, how much oil and how much gas we have. Before we close, any question? No? Okay, then see you on Monday.